All right, guys, we're going to go ahead and take a look at the review for Unit 5. Okay, and we're going to make some notes. I have my separate sheet of paper out here because it sure did not give us a lot of room. We're going to make some notes here as we go through this, though. When you guys see find the absolute maximum minimum, here's what I want you to remember, okay? Absolute means that we're going to test critical numbers and endpoints. Okay? Now, it gave me the endpoints. These are kind of weird endpoints, but it did give me the endpoints right there. And then it says find the critical numbers without using a calculator. I think what that means is these are so lousy to plug in that we can use a calculator to actually do, the candidates test. Once we find the critical points and the endpoints, we're going to put it in a table. This is called the candidates test, and we just look at the y values for the highest and for the lowest, okay? All right, so here's my equation. Here it goes. 3x to the fourth plus 4x to the third minus 12x squared plus 5. Here we go for our critical points. This is going to be 12x to the third plus 12x squared minus 24x. That cancels out. We set this equal to 0. I can factor out a 12x. So I have x squared plus x minus 2 is 0. When I factor that, I get x plus 2, x minus 1. And my critical numbers are from here, 0, from here, -2, and from here, 1. And I have to test my critical numbers along with my endpoints. Remember, my endpoints are -5/4 and 5/4. Now that's like 1 1/4, right? Okay, what that means is that actually this is outside my interval, so I'm actually not going to test -2. That's not in between these numbers. This is why I like making the table so that these numbers go in order. 0, 1. Okay? Real quick, I am going to calculate. You guys can do this too. Plugging in 5/4. Third, okay, into the original equation, right? Squared plus 5. And I get, this one, 1.386. And then I'm going to plug in -5/4. Hopefully I did this okay. And negative for this one. Okay, and I get -14.238. When I plug in 0, I get 5. And when I plug in 1, I get 0. Right? So when I look at this, my highest number is 5. So I have an absolute max equal to 5. You could say it's at x equals 0, but the max actually equals 5. And then, nope, my absolute min is this like -14 right here. So it's at x equals -5/4, and the absolute min equals -14.238. Okay, so the y values are pretty much what we're going to put for our answer here. All right? All right, you guys, let's go ahead and look at number 2. This asks us for a lot of stuff, but the kind of nice thing is it gave us these derivatives. It lets me have a minute to not have to calculate each one by quotient rule and simplifying whatever. Okay? Remember from the original problem, we can find domain. We can find x-intercept, y-intercept, vertical asymptote, and we can find end behavior, which a lot of times means horizontal asymptote, or if it has a slant asymptote, if it goes to infinity, stuff like that. Okay? And then the first derivative will give me relative extrema, so I'll do that for the first derivative. And then the second derivative will give me points of inflection. Okay? But let's just start with all this stuff first. My domain is all real numbers, except x cannot be 0. Why? Well, because there is a vertical asymptote at 0. So I'll go ahead and write that up. Okay, do you guys remember the x-intercepts when we have a fraction, particularly, is when the top equals 0. Y-intercept is where we plug in 0. If I let the top equal 0, I actually can solve that. So x to the third equals -2. So the x-intercept is the cube root of -2. Kind of crazy, but that's going to be a little small, decimally negative number. And if I plug in 0 for y, if I plug in 0 here and here, you guys, I end up getting 2 over 0, which is undefined. Okay? Okay. And because I don't have the premium version of this software, every 10 minutes it's going to cut me off and I have to restart it. So where was I? Oh, there is no y-intercept. Okay, you guys, now end behavior, let's kind of remember this. This is what happens as my limit goes to infinity. Well, the top is bigger than the bottom, so that goes to positive infinity. What about as I go to negative infinity? Well, I really just have to check the signs here. A negative to the third is negative over a negative, and a negative over negative is positive, so that also goes to positive infinity. Okay, so it looks like both of those, the end behavior, that would be the end behavior right there, is that they both go to positive infinity. Okay, cool. Let's go ahead and work with our first derivative now. Again, they already found it for us over here, so I'm just going to use that 2x to the third minus 2 over x squared. Now on my sine line graph, that asymptote at 0 is going to continue through the whole problem. And in order to find my critical points, I need to set this equal to 0, but more or less that's just the same as setting the top equal to 0. Okay? And so I end up getting 2x to the third equals 2. X to the third is 1. X is 1. All right. Now, when I do test points, okay, here's the thing. The bottom is always going to be squared, so I'm really just plugging into the top. Let's plug in a negative number, like -1. -1 to the third is negative. That's negative. Let's plug in a number like between 0 and 1, like a half. Okay, a half to the third is an eighth. 2 times an eighth is a fourth. That's negative. And then if I plug in a number bigger than 1, like 2, let's say, if I plug in 2, 2/3 is 8 times 2 is 16 minus 2. That's positive. All right? So it looks like what it's doing here is it's going decreasing and then decreasing, increasing. Okay, with an asymptote there. And so I have a relative min, because it asks for the relative extrema, at the point 1 something. The way that I get the y value is I plug it back into the original. If I plug in 1 right here, I get 3 over 1. So this is at the point 1, 3. Okay? Okay, now I'm going to do my second derivative. My second derivative is 2x to the third plus 4 over x to the third. Again, I have a asymptote at 0. And again, when I set the top equal to 0 to solve that, I can actually solve that because it's an x to the third. X to the third is -2. X is the cube root of -2. Where have I seen that before? That was my x-intercept. And so I'm going to put that here. It's a negative number anyway. Okay, this is a little bit tricky. I'm going to go ahead and say, what is the cube root of -2? And it's like -1.25. Okay, so I know it was -1 point something. You don't really need to know that for your sine line graph because, okay, check it out. I know that this is like, that if I were to pick a number bigger than it, I could pick like -5 or something. That would give me a huge negative divided by a huge negative, so that would be positive. But if I were to pick a number right here, let's say I pick -1, okay? -1 would be -2 plus 4, it would be positive divided by negative. And then let's say I pick like 1, that would be a positive divided by positive. Okay? And so this goes concave up, down, up. All right, this is crazy. I don't know what this looks like. We're going to just try to sketch it because I've done everything I needed to do here. Oh, and so I should say, actually, I got my concavity, but this thing has an inflection point at the cube root of -2. And what's the y coordinate for that? I already know it's 0 because I found out that that was a intercept. Okay, so I have an asymptote at 0. Okay, so there we go. And then I have a point at 1, 3, and then I have a point at negative cube root of 2, 0, which is like 1.25. It's probably about right there. Okay, and I'm going to start by just following my decreasing. It goes like decreasing, and then it goes decreasing, increasing, right? And then if I'm going to like actually graph it, make that a little bit bigger. Okay, I'm going to get, oh, it's concave up to concave down, and then this is like concave up all the way through. That's crazy, but my end behavior does show that. That all shows it, so okay. I'm interested to see if I'm right or not. Let's look. X to the third plus 2 over x. What the heck? Look at that. Concave up, concave down, then a little guy over there. Pretty amazing. All right, that was good. Okay. Let's move on to number 3. Without using a calculator, find the intercepts, local extrema, points of inflection, and draw a graph of absolute value of negative x to the third plus 3x squared. Hint, first graph the same function without the absolute value. Okay, check it out. If I were to graph this, guys, just very basically without the absolute value, I would find my zeros. And if I factor out, I'm going to factor out negative x squared. I know I have x equals 0 and x equals 3 is where it crosses. Also, do you guys remember this? Because this came from an x squared, that means that this has what's called a multiplicity of 2 and it bounces on the graph, whereas this one will cross. Okay, like we learned that in Math 3, so we got a bounce cross. And then the other thing we learned is because it starts with a negative, the end behavior, and I could just plug in, but I know the end behavior goes like that to that, right? Yeah, that's right. Okay, so look, here's how it goes. It's going to start up here. It's going to bounce, cross. Okay. Now that's the graph of negative 3x to the third plus 3x squared, right? So let me graph this in here. Negative 3x to the third plus 3x squared. Okay, so you see it bounce and a cross. Oh, hold on. It was not a 3 right there. It's just negative. Okay, there we go. It's 0 and 3, right? Now, if I'm going to put the absolute value around it, you guys, what's going to happen is anything on the bottom is going to go up. Okay? So, if I absolute value this whole thing, look at how it's still going to bounce there, but it's going to like bring that part up. Okay? So, I'm going to go ahead and make this my new graph. I am going to erase everything from there down. And I'm going to make it go like that. Okay? All right, blah, blah, blah. Okay, so find the intercepts. So I'm just going to kind of list this stuff. This has x-intercepts at 0 and 3. It has a y-intercept at 0, 0. Local extrema, it has relative mins at 0 and 3, and then has a relative max right here. Well, you guys, that point right there is the same whether or not I do the absolute value. It's still the same. So what I'm going to do to find that is I'm going to take the derivative of the one without the absolute value, honestly, because we can't really take derivatives of stuff with absolute values. Not easily, anyways. All right, pause. Okay, chill. So my derivative is negative 3x squared plus 6x. When I set that equal to 0, I get x equals 0 and 2. Well, x equals 0 is that one, x equals 2 is that one. Before, remember, it went down like that. So when I did the absolute value, it did create a new relative min there. But anyways, I do know that this point now is at x equals 2. So I have a relative max at 2 something. Let's go ahead and put that in. Relative max at 2 something. If I plug that into the original problem, I get negative 8 plus 12. So at the point 24 is a relative max. Okay. And then I'm basically going to go through the same thing with my concavity. All right. So like, what is this? This is number 3. Okay. So yeah, for my point of inflection, I'm going to take the second derivative from here, which gives me negative 6x plus 6. And so it looks like I have a point of inflection at x equals 1. So I'm going to say I have a point of inflection at the point 1, 2 is where that is. Okay, now look, this, if I look at it, is concave up, holds water, and then this is all concave down. And then that goes up to concave up again. Okay, so let's see. Actually, hold on. Changes at 1. What am I doing? Just a sec. I didn't quite draw right. Hang on. Okay, concave up to there, and then concave down, and then concave up. Okay? Which kind of tells me that there's actually another point of inflection at the point 3, 0, because it's changing from concave down to concave up. All right. Cool. That was fun. Okay, let's look at number 4. Again, it gave me multiple derivatives. This is making me feel like there might be a question like this on your test, right? Where it gives you all the derivatives and you have to find everything. Okay. We have x square root of 16 minus x squared. Cool. The domain on this is super interesting, you guys. There's no dividing by 0, but if I try to put, whatever's inside the square root sign, I can take the square root of positive numbers and I can take the square root of 0. Now, you actually can't solve this like a normal equation. You're not allowed to like move the 16 over, divide by a negative. You're not allowed to do that. What you do have to do, I know this is 4 plus x, 4 minus x. This is a sine line graph that I'm using before I even get to a derivative, just to find the domain, okay? Because what happens here is if I plug in like negative 5, okay, that makes that negative, that makes that positive. That gives me a negative number. If I plug in 0, 4 plus 0, 4 minus 0, that's positive. And if I plug in 5, that's 9, and negative 1, that's negative. Well, in order for this domain to exist, the numbers under the square root have to be positive. So this has a domain of negative 4 to 4 only. Okay? It's kind of a weird problem there, but that's my domain, negative 4 to 4. Okay, and then, intercepts. Where does this equal 0? Well, you guys, I'm going to look at two things. I'm going to look at where does x equal 0, and I'm going to look at where does the square root of 16 minus x squared equals 0. Well, that one is already solved. This one I also kind of already solved. I can square both sides, but remember I just got x is plus or minus 4. So those are my x-intercepts. 0, 0, 4, 0, negative 4, 0. If I'm looking for my y-intercept, it's when I plug in 0, and that's just 0, 0 also. Okay, so right now I have x-intercepts here, here, and here. And then my domain doesn't go past those like negative 4 and 4. All right? Cool. Now my first derivative, it gave it to me, was, here we go. 16 minus 2x squared over the square root of 16 minus x squared. Okay, well again, I'm really just looking for when the top equals 0, the bottom only equals 0, 4 and negative 4, those are my endpoints. So I'm trying to solve this. Well, if I get 16 equals 2x squared, 8 is x squared, so x is plus or minus square root of 8. If I make a sine line graph, and this time, you guys, my sine line graph only goes from negative 4 to 4 because that's the interval that I'm on, okay? Square root of 8, let's see, square root of 8 is going to be like 2 point something. So if I plug in negative 3, I'm going to get 16 minus 18. I'm going to get a negative. The bottom's always positive because you're square rooting, okay? If I plug in 0, I get a positive over a positive. And if I plug in 3, I get a negative over a positive, okay? So I have, let's see, this is going to go decreasing, increasing, decreasing. And so I have a relative min at negative root 8 something and a relative max at positive root 8 something. If I plug those into here, let's see what I get. The square root of 8 squared is 8. So it's going to be square root 8 times square root of 16 minus 8. So it'll be square root 8 times square root 8, which will be 8. That's kind of fun. And for negative, for negative, I think it'll be negative 8. Square root of 16 minus 8, it would be like that. Yeah, it would be negative 8, okay? Square root of 8 is like 2 point something. So negative 2 point something, negative 8. Positive 2 point something, positive 8. And right now I know that it goes decreasing, increasing, decreasing. Okay? Now I'm going to do my second derivative, which it told me is this. All right. Again, setting the top equal to 0. Okay, so I might as well factor out a 2x. So I have x squared minus 24 is 0. So I end up getting x is 0 and plus or minus the square root of 24. On my sine line graph between negative 4 and 4, the square root of 24 is going to be just under square root of 25. The square root of 25 is 5. Oh, so, hold on, did I do that right? So shoot, those don't even count, right? I crossed off the wrong thing, but yeah, the square root of 24, that's outside of my interval. That's not even like possible, right? So I really just have a point at 0. Oh, that makes this so much easier. Okay, so let's say I plug in negative 1. That's going to be negative 2 plus 48. So that's positive. And let's say I plug in 1. That's going to be 2 minus 48. Excuse me, that's going to be negative. And so my concavity is going to go concave up, concave down. And I have an inflection point at 0 something. Well, when I plug it in here, I get 0 times the square root of 16. So it's 0, 0, which was already a point. So that's chill. And so when I go to draw this thing, right, it goes decreasing to increasing, concave up, and then increasing to decreasing, concave down. Okay? So let's take a look and make sure that this looks right. There you go. Okay, and I got a relative max at that's square root of 8, 8, negative square root of 8, negative 8, inflection point at 0, 0. Pretty chill, pretty chill. Okay, and then sketch the graph. Cool. All right, for number 5. Find the intercepts, relative extrema, and points of inflection, and then graph without using a calculator. So much curve sketching. Okay, let's do this. All right, y'all, here we go. My x-intercepts. If I set this equal to 0 and I factor out an x, my x-intercepts are at 0 and plus or minus square root of 3. So I have points at 0, 0, and root 3, 0, and negative root 3, 0. Okay? My y-intercept, when I plug in 0, is at 0, 0. Let's go ahead and go to my first derivative. This is going to be 3x squared minus 3. And I'll go ahead and factor this all the way out because it's a difference of squares. I get x plus 1, x minus 1. Okay, so my critical points are at plus minus 1. And I'm going to go ahead and test them into the derivative. And I think I'll test them into this one that's nicely factored out for me. And so when I test in like negative 2, that makes negative negative, which is positive. When I test in 0, that's positive negative. And when I test in 2, it's positive positive. Okay? And so it goes increasing, decreasing, increasing. And it wants my relative extrema. I have a relative max at negative 1 something. I have a relative min at 1 something. Okay, remember, the somethings I get by plugging in right here. If I plug in negative 1, I get negative 1 plus 3, which is 2. If I plug in 1, I get 1 minus 3, which is negative 2. Okay? So if I'm going to graph this, let me just go ahead and start. I have zeros at 0. Square root of 3 is about 1.7. I just know it's like somewhere between 1 and 2, and that's fine. And then I have relative maxes at negative 1, 2, and 1, negative 2. So far it's looking like it goes, right? Something like that. Okay, when I do my second derivative, I'm going to go off of that. I just get 6x, which equals 0 at 0. And then that's a pretty easy one to do. If I plug in a negative, I get negative. If I plug in a positive, I get positive. So this goes concave down, concave up. And I have an inflection point at 0, 0 when I plug that in. Sort of makes sense to me because that's what I was thinking that this was going to look like, right? Because it's going to go concave down, concave up. Okay. Not bad, not bad. All right. Okay, now 6 and 7. Let me go ahead and do it on here. Okay, guys, when you're going forward, all you're doing is you're just thinking about slopes, okay? So I'm going to go forward. I'm going to go to the graph of f double prime first, okay? And the first thing I notice is that the slope is 0 at 1 and 3, and something's going on at 4, right? So at 1, it's 0. At 3, it's 0. And I'm just going to put a question mark because something's going on. I don't really know. Okay? These are positive slopes, so they're above the axis. These are negative slopes, so they're below the axis. And then these are positive and then still positive. But let's look at what's happening here, you guys. That slope right there is maybe like 1/10. Okay? That slope up there, that's a huge slope. That's like 10. Right? So it's small numbers going to really big numbers. Okay? And I feel like maybe they're This is one possible way to do it. There could be like an asymptote right there. And then again, this is a slope, like a really big slope, like -10, and then it keeps on like going down, down, down. Oh, actually, you know what? This looks linear. Is this linear? This is linear. Check it out. That has a slope of -3. So at here, I would just go at -3 and go over. Okay? And so I think I would draw the second derivative as something like that. Okay. Around 6. Just make sure I'm not like missing anything here. Okay, perfect. Now that might not go to an asymptote. Also, it could just go to like an open circle or something like that. Okay, but otherwise we're good. And because this one has an arrow on the end, we do want to put an arrow on the end of that one. Okay, now going backwards, you guys know that this is a lot more tricky. Going backwards to f of x, because I can't do it without sine line graphs. Okay, so let me erase some of this stuff I've already got going on here. And I'm going to make a sine line graph of f prime. Now this is interesting. It's got an arrow on this side and then a bracket on this side. Anyway, and I want to see where f prime actually hits 0, and it happens at 0 and 3. And before that, it's negative. And then in between there, if I did test points, it's positive, and in between there, it's positive. So this is actually going to go decreasing, increasing, increasing. Okay. Now I'm going to do a sine line graph of the second derivative. Now I could use this second derivative over here, or I could just continue looking at this. Usually if you're going backwards, though, you're not going to have drawn that first, so I'll just go to there. Okay. The second derivative is the slope of the first derivative. The slope at 1 and 3 and then at 4 is like undefined, but it's still there. And so what's happening is these are positive slopes leading up, negative slopes, positive slopes, negative slopes. Okay? And so my function goes concave up, down, up, down. So starting at 0, 0, and that's a relative min. So actually it's just going to go down and then up. Okay? Now, at 1, I have an inflection point. At 3, I have an inflection point. And at 4, something's happening. Okay, so it's going to go concave up, concave down, and then I'll go concave up from 3 to 4. Okay. And then it will go... It'll keep increasing, but it'll go like concave down again. That'll stop, that'll go. Okay, something like that. These are kind of more like touchy-feely kind of graphs. Just make it look about right, and you're good to go. All right. Okay, perfect. This is 30 minutes, so I think we're going to stop here for part 1 of sketching, because then we're going to start getting into relative maxes and mins. All right, so we'll stop it here, and I'll do another part.